Hey guys, if you missed class or you need a little refresher here, this video is going to explain what we did in class on Tuesday. We are going to construct our own angle tools. So like this picture that you're looking at here are all these angles all the way up to 360 degrees. We're not going to do these exact angles, but we're going to make our own measuring tool. And we're going to construct it from a compass and a straight edge. And we're going to construct exact angle measures without actually measuring them. We're going to just, with no protractor, it's kind of like we're making the very first protractor. There isn't one yet. So we're going to make it, and we're going to use some math relationships and our construction concepts to do that, okay? So before we can get going on this project, there's a couple constructions that we have to think about. So in this video, I'm going to explain to you how we can construct an equilateral triangle and we can construct an angle bisector. So all that this means is if you have any angle, you can just cut it in half, no matter what the angle looks like. Okay? When we do this, please make sure that when we construct, you can follow the logic behind the construction, because that's really what's important. Because if you know the logic, you can do the steps. So let's talk about constructing an equilateral triangle here. So here is an equilateral triangle. And in an equilateral triangle, we know that all three sides have to be congruent, right? So we know that these sides are congruent in length. That's the definition. So how can we reason this? Well, if you have a compass, I can, set the center point on one end point and my pencil or whatever on the other, and that distance is really measuring that segment length, right? And so as I measure this, notice this point B is also that same length there, right? So if you think about using a circle, doesn't that verify that this segment right here has to be equal or the same length, because aren't those radii of the same circle? And now how do we argue that this is the same as these two? So don't we do the same thing? I'm going to put one point on the center, and now if I use the same exact radius, then now I can measure another circle here, right? That guarantees us that since this is the center of our circle, then this red segment that I have and now this red segment that I have to be the same length, because they're radii of the exact same circle as well. Okay? So, since we made our circles the same, we didn't change the radius here, we can argue that from this circle that this segment is congruent to this segment, and then also from this center of this circle that this segment is equal to this segment. Therefore, that's always going to make an equilateral triangle. So let's try that construction without having a triangle already there. So let's construct an equilateral triangle again. So I'm going to grab my compass. Your straight edge is just going to have you make, sides. So what we need to start with is a segment length, right? So a side of a triangle. Then all that we have to do really is just grab our compass. I'm going to make one of the endpoints the center of a circle, and I'm going to make the other endpoint, a point on the circle here, and I'm going to go ahead and just make a circle. And it doesn't even have to be the full circle, okay? And then all that I'm going to do is just flip my compass and make this endpoint now the center of a circle. This is now going to be a point on the circle. So when I make my circle here, that our triangle is really just formed from the two endpoints of our circle, of our segment, and then connect the two other sides as sides that connect the intersection of our circle. And again, our logic says if this is the center of a circle here, then this segment is a radius, so it's got to be congruent to this segment, which is also a radius. But because we kept that radius the exact same on both circles, we know that this is a radius of this right circle, and so is this, right? So those have to be equal. So that's how we construct a 60-degree angle, right? Or, an equilateral triangle. Now, we also know that in an equilateral triangle that all these angles are going to be the same, right? we'll prove in class that if you add up the three angles in any triangle, no matter what the triangle looks like, that their sum is always going to equal 180 degrees. So in an equilateral triangle, if all the angles are going to be the same measure and they add up to 180 degrees, each angle has to be 60 degrees. Okay? So if you think about our angle finding tool and constructing an equilateral triangle, not only did we make this triangle here that has three equal sides, but we also made a 60-degree angle, and we're guaranteed that it's a 60-degree angle without even using a protractor, right? Although if I do use a protractor, we can confirm maybe that we made a 60-degree angle. So I'm going to put, the vertex on one of the points here. I'll try to make one of the, how do I rotate? There we go. Make one side, the 0 line, and then we open up and check that out. This angle between 70 and 50, that's an exact 60-degree angle. Okay, so not only can we construct an equilateral triangle, but we're actually constructing an angle measure of a precise value, 60 degrees. So if we ever want to make a 60-degree angle, all we do is just do our quick little construction here of an equilateral triangle, because we guarantee that the angles within that are 60 degrees. Okay, so that's one of the main concepts we need to go or have for this measurement tool, is measuring or constructing an equilateral triangle. Now let's construct an angle bisector. So given any angle like this here, we want to cut this baby right in half. Okay, so how do we do that? How do we logically and for a fact know that we can do this without this look-like argument? And the idea here, when we talked reflections and rotations, we had some isosceles triangle thoughts going in here. That if you take, so this is an isosceles triangle, right? We know that that segment's congruent to that segment. If we bisect the base at a perpendicular relationship, right, 90-degree angle, then we know that that segment has to go through the opposite point, right? So what that allows us to talk about then, and this is our discussion that we had in reflections, that when you take this isosceles triangle, we cut it this side in half and perpendicular, hence perpendicular bisector of the base, then it creates two congruent triangles, right? This left triangle is a right triangle that looks just like this right triangle, this right triangle looks just like this right triangle, and if we folded the triangles on this line, they would map up exactly, right? This segment that's the same length as this would map onto each other. This segment would map onto this. This 90-degree would fold right onto this 90-degree angle. But more importantly, this angle up here and this angle up here must be the same, because this angle is just going to fold right on top of this angle here. So what we can kind of pull out of this is our idea that we want to construct. We want to make an angle that gets cut into two equal sections, right? Hence bisect. Two cutting into two equal sections. So what we have to have for this relationship is an isosceles triangle, and then we just need the perpendicular bisector of the base, and that'll get us a bisected angle up here. Okay, so let's see if we can try to make this happen. We need to construct an isosceles triangle. So I'm going to grab my compass tool. I'm going to put the center of my compass right on the vertex of my angle, and I'm going to just make some radius. It doesn't matter where. We can make a small circle, big circle, whatever. Just make a circle that intersects our angle on both sides, because now if we make this point here and this point here, isn't from the vertex to this point, vertex to this point, they have to be the same because they're radii of the same circle, right? So what we really have is this isosceles triangle. Here's our third side here, and we don't have to draw it. If we draw it, we can definitely see the triangle now. But if we don't draw it, it's still the same relationship. We want to perpendicularly bisect the distance between these 2 points, or the segment between them if we drew the segment. And we should know by now how to do the perpendicular bisector construction. Again, don't all that we do, I'm going to put the center on one of these points. I'm going to perpendicularly bisect this distance. So I'm just going to create a radius, and I could use this other point, that's fine. And I'm just going to do a circle, flip my compass, and do another circle. Oops, I should probably move this. And I can do another circle now, right? So, where those two circles meet, remember, forms the perpendicular bisector to this distance, even though we don't have it drawn here, right? So that's our perpendicular bisector construction. But if we extend this segment, it actually goes through the vertex too, and there's our angle that gets bisected, gets cut into two equal angles here, okay? So the first step that we got to do, create an isosceles triangle, or get these two lengths right here to be the same with this first circle, and then use the intersections now on our angle and that circle as the base of an isosceles triangle, and make the perpendicular bisector, which really ultimately is going to bisect our angle here. Okay, so please be able to construct some equilateral triangles and some angle bisectors, because those are some big concepts that we need to have when we make our angle tool.